Hey, welcome back to Calculus. We're going to do a second example from section 4.7. This one's going to involve some three-dimensional geometries and three-dimensional shapes. In particular, we want to find the dimensions. That's going to be the question, the dimensions of the right circular cylinder with a fixed volume of 1,000 cubic centimeters, or 1 liter if you prefer, and its surface area is minimal. All right, so again, a lot to unpack here, finding the dimensions of something. So we're going to say how big it is in some sense. What is that something? Well, it's a right circular cylinder. So we'll have to know what that is. Yeah, so it's like a soup can. So it's a cylinder whose height is perpendicular to its base. Its base is a circle. We want that can to have a fixed volume of 1,000 cubic centimeters, yeah, but we can change the height and the radius. That's what I mean by the dimensions. The height and the radius can change, keeping that volume fixed at 1,000, but what will end up changing is the surface area of the can, and we want to know, well, what is the smallest surface area? Let's switch over and look at an animation to try to help us visualize this problem. Got a nice one I made for you, I think. So here you're looking at a right circular cylinder. All right, so it's got circular bases. It looks kind of bluish in this picture, and then the cylinder side looks kind of orange. It's got a circular base on top and a circular base on bottom. And suppose that that thing holds 1,000 cubic centimeters. All right, so I can change that cylinder's dimensions. I can, for example, make it have a bigger radius. And in doing so, I had to shrink the height of it to keep the volume fixed. All right, so it's the same kind of phenomenon we were looking at before, or with inscribed rectangles, is I can make one of these dimensions bigger. I have to make the other one smaller to keep the volume fixed. All right, so this cylinder that you're looking at, it looks like it might have a much larger surface area than the original one because I'm making these circular discs that make up the top and the bottom of the cylinder bigger. And the area of those disks increases as a quadratic function of the radius. Yeah, so by making big disks, I make the surface area big. I can make the surface area smaller by decreasing that radius, but decreasing the radius makes the height get bigger, and that's going to add some surface area. So somewhere in between, here you can look at a super tall, skinny cylinder. It's going to have a big surface area. Yeah, the volume is the same. So somewhere in between these super tall, skinny ones and these kind of shorter ones with bigger radii should be the optimal answer. And that's the question that we're trying to answer. It's like, well, what would the height and the radius have to be if we were going to try to make that surface area as small as possible? Okay, so let's switch back to the whiteboard. I hope that was a useful demonstration, at least just trying to understand, like, what is the question that we're trying to answer? Okay, so we'll switch back to the whiteboard surface here. Sorry, there's a little delay. Here we go. Good. So let's go about trying to coordinatize this problem. So we got to talk about a right circular cylinder. I've got one drawn there. A right circular cylinder has two kind of measurements, two things that dictate its volume and its surface area. One of them is its height. We're measuring that in centimeters because the volume was in cubic centimeters. I'm denoting it by H. And if the volume is 1,000 cubic centimeters, then H can't be 0. All right, so the height of that cylinder has to be something positive. And then a cylinder has also got a radius. Yeah, the radius is also measured in centimeters. It also has to be greater than 0. The volume of a right circular cylinder, you might remember, is the area of the base times the height. So pi r squared h is the volume of that cylinder, and we're setting that equal to 1,000. That's our constraint equation, if you like. Okay, pi times r squared times h is 1,000. We're going to have to use that constraint equation to eliminate one of the variables rh, so that our one variable calculus machine will work. But what about the surface area? We could look it up. I mean, I just kind of gave you the formula for the volume of a cylinder, but the surface area of it, I kind of wanted to have at least a brief discussion about. You can kind of dissect a cylinder into pieces and recover the formula for its surface area. So let's take a look at this diagram I've got here. I'm trying to show you that if you take that circular cylinder and imagine like removing the top and the bottom into these two circular pieces. Okay, so I take the top off. and I put it down here, it's a circle of radius r. I take the bottom off, I put it down here, it's a circle of radius r. And then what would be left was just the cylinder side. And imagine slicing that cylinder side, take a pair of cylinder scissors and cut it straight up and down that way, where I just drew that red line, and then kind of unroll it. You can do this with a piece of paper. Take a piece of paper on your desk and roll it up so that the edges of the top and bottom of the paper touch to each other, and you'll make a cylinder side. It won't have a top and a bottom, but it's a cylinder side. So over here on the right-hand side of the picture, I've shown what that cylinder side looks like if it's unrolled. And well, what are its dimensions? One of its dimensions is the height of the cylinder. That's along this incision that we made. It has height h. But the other dimension is in the cylinder, it's the circumference around. The circumference around becomes this horizontal length over there when you unroll it. So the circumference of a circle of radius r is 2 pi r. So that's why this length of the rectangle over here is 2 pi r. All right. Well, so now we can add them up. The area of a circle, pi r squared, plus the bottom, pi r squared, plus this rectangle, which is 2 pi r by h. Add all of those things together, and you get the surface area of a cylinder. All right? Cylinder with base radius r and height h. Here you can check my algebra. I'm kind of writing it in this form, 2 pi r times r plus h. R and h are both positive. But we can't have a function of two variables. We need to have one, so that's when we're going to use our constraint equation. We said that the volume was fixed at 1,000. If I solve that for h, the algebra is easier if I solve it for h, and then I'm just going to plop that h in right there. Then I'll have the surface area as a function of r alone. All right, so you can stop the video and do the algebra if you want to, but here's the expression that I arrive at. So I just replaced h with this expression, 1,000 over pi r squared, did some algebra and rewrote my surface area then as 2 pi r squared plus 2,000 over r. R is positive. That's the objective function. That's the function that I want to minimize. So how do I minimize it? I don't have endpoints in this example, so I'm going to take its derivative and make a sign chart. Stop the video and differentiate this thing on your own. Put it into a nice form for answering questions like when is it 0 and when's it undefined. Okay, I'm just going to proceed. Here's my calculation of the derivative. 4 pi r is the derivative of 2 pi r squared. 2,000 over r is like 2,000 times r to the negative 1. So I'm differentiating with the power rule. And then I just got a common denominator. Put that in the form of a fraction. This fraction is undefined if r is 0, but r is not allowed to be 0. So the only critical points we have to consider is when the derivative is equal to 0. That's only when the numerator is equal to 0. And if you do the math out, you get that the r value is the cube root of 500 over pi. It's the exact value. It's approximately 5.4, and that would be centimeters. If you're going to do further calculations, though, you want to make sure to use this exact value for r, not a rounded value. You don't ever want to do subsequent calculations with a rounded value because your round-off error will get bigger and bigger. Okay? So what do we got to do now? We got to make a sign chart. I got to take that one and only critical value and put it in my sign chart down here. And you can check my signs that when r is less than that critical value, the second derivative is negative. And when r is bigger than that critical value, the second derivative is positive. So a sign diagram that looks like that tells us a function was decreasing and then increasing. So the first derivative test tells us that we've got a local minimum and hence a global minimum because it was the only critical point. Got a global minimum at r equals this cube root of 500 over pi. Okay, the original question was what are the dimensions of the cylinder that minimizes it? This is sort of half the answer. I know the radius. We have to go back and recover the fact that h, we said, was equal to 1,000 over pi r squared. So if you replace the value of r in there, cube root of 500 over pi, I'm going to leave the algebra to you. That simplifies nicely to 2 times the cube root of 500 over pi, or 2 times h. Right, so 2 times h, so 2 times that cube root, or approximately 10.8. And again, the units there would be centimeters. Right, it's an interesting fact, actually, that the surface area is minimized when the height of the can is precisely 2 times the radius. Okay, so the last thing to do is to write up our answer in a nice complete sentence. The dimensions of a right circular cylinder with a volume 1,000 cubic centimeters and a minimal surface area is R. I'm just going to say the rounded values in my answer. R is approximately 5.4 centimeters and H is approximately twice that, 10.8 centimeters. All right, I hope that was a useful and fun example. I'm going to make one more. Thanks for listening.